So we have the rational root theorem that's going to help us figure out the roots of a polynomial when we can't use standard factorization techniques. For example, with this polynomial right here, we can't factor it. So the rational root theorem says that the list of possible, and that is key word, okay, not guaranteed, but possible rational roots would occur at factors of the constant term divided by factors of the leading coefficient. So remember, leading coefficient is the number in front of the highest degree term. So in this example, the leading coefficient is 1, and the constant term is the number without any variable associated with it. So like in this case, that's a 10. So the constant is 10. So we're looking for all the possible factors of the constant. So we need to list all of the factors of 10. So when I want to make a list of factors, I like to make a little table. So, and that's a 10 there. So 1 goes in 10 times, 2 goes in 5 times, 3 doesn't go in, 4 doesn't go in, 5 goes in 2 times, and I already have it. So now I know I have the complete list of factors. But in addition to that, -1 and -10 would also be factors, right? If you multiply -1 times -10, you get back to a positive 10. So all of the possible factors of the constant, so I want to list all the factors of the constant term, that would be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. And all of the possible factors of the leading coefficient would just be plus or minus 1. So how do I write this as a ratio? So all the possible rational roots, right? If I wrote that as a list, it would be all the possible factors of the constant divided by the factors of the leading coefficient. Well, if I take plus or minus 1 and I divide it by plus or minus 1, I'm still just left with plus or minus 1, and then again plus or minus 2, plus or minus 5, and plus or minus 10. Okay, so now what we're going to be asked to do is to find all of the zeros for this polynomial. So I'm going to leave that possible roots right there. So we want to find all the zeros for this polynomial and then use these zeros and the leading coefficient test to sketch the graph. So now to decide which of these possible rational roots are actual rational roots, we're going to go ahead and graph this. And I'm okay with us using technology for this purpose. There's a way to do it by hand. But so when I look at this polynomial, I see that it does have a root, and that root is at -2. And based on the fact that it's cubic, I can see that this function's never coming back down. So this is the only root that we see. So that's telling me that -2, 0 is an x-intercept, or -2 is a root. So if -2 is a root, that's telling me that p of x should have as its factorization an x plus 2 times some other stuff, right? Something of degree 2. But I have no idea what that is, and certainly the graph's not going to help me do that. So what I have to think about is somehow this polynomial, so let's write this polynomial equals x plus 2 times something. How do I find that something? Well, algebraically, I just divide both sides by x plus 2. Right? So this leads to the idea that if I want to know what the complete factorization of this polynomial, I would have to do long division of polynomials to actually decide how to completely factor. Now, why should I do this? Whatever this question mark is, it's not producing any real roots, but if we're trying to find all zeros, including imaginary ones, we do have to factor it completely, and then we'll need to use quadratic formula on this part. So let's go through this process. Okay, so I want to divide x plus 2 into x cubed minus x squared minus x plus 10. Just to remind ourselves of what long division looks like, say, for example, we were trying to divide 7 into 245 or something like that, right? How would we start this? We wouldn't try to do the whole thing. We would say, how many times does 7 go into, well, we can't go into 2, so we would go the first 2 digits, 7 into 24. So that goes in 3 full times, and 7 times, so then we'd multiply 7 times 3, and put the answer there. We get 21. And now I'm not liking this little line right here, so I'm going to erase that. We would do 24 minus, I'm sorry, and you know what? I'm not even liking this little arrow here, right? So you're just following along. Don't look at the arrows. Okay, so we'd multiply 7 times 3, we get 21. We would then subtract 24 minus 21 would give us 3. Now 7 doesn't go into 3, so we carry down the 5, and then 7 goes into 35. 5 times. Okay, so that tells us that 245 divided by 7 is 35. Let's do this same computation, a parallel computation with this. So I'm looking at asking myself, how many times does x plus 2 go into x cubed? Well, it's not going to go in evenly, but I know to get x to be an x cubed, I have to multiply it by an x squared. So the first term is going to be x squared. Then, just like before when I multiplied the 3 times the 7, I'm going to multiply the x squared times the x plus 2, which means by distributing, I'm multiplying it by both those terms. So I multiply x squared by x gives me x cubed, and x squared times 2 gives me 2x squared. So again, just like over here, I subtract, I'm going to subtract. And when I subtract, I want to remember that I'm subtracting that entire term. So I'm going to be subtracting the x cubed and subtracting the 2x squared. So x cubed minus x cubed is going to give me 0. But x squared minus 2x squared is negative 3x squared. Watch that sign, right? Negative x squared minus 2x squared is negative 3x squared. Okay, and then now we can pull down the next term and ask ourselves, how many times would x plus 2 go into this expression? So again, to get x to be multiplied to give me, what do I multiply x by to get to negative 3x squared? That's going to be a negative 3x. And so now I take this 3x and I just multiply it by x and 2 so that I can get the next row here, right? Now we didn't need multiple levels over in our example, but so negative 3x times x is negative 3x squared. Negative 3x times 2 is going to be negative 6x. So again, I now want to subtract, and when I subtract, I'm subtracting that entire term. So that's going to go away, right? Because this would be a negative 3x squared plus 3x squared. Here I've got a negative x minus a negative or plus 6x. So that's going to give me 5x. And then again, I carry down the next term and ask myself, finally, how many times does x go into 5x plus 10? And the x goes into 5x 5 times. And so finally, I multiply the 5 by the x and the 5 by the 2. And so I get 5x plus 10 with no remainder. So that tells me, finally, that if I divide x cubed minus x squared minus x plus 10 divided by x plus 2, I get x squared minus 3x plus 5. So when you go back to the factored form of p of x, we just found this sort of question mark, right? That question mark is x squared minus 3x plus 5. Okay, so solving now for the zeros, to find the zeros, if we solve p of x, set p of x equal to 0, we have got two possibilities. Either x plus 2 is 0, or this quadratic x squared minus 3x plus 5 is 0. This one, of course, gives us the 0 we knew by Desmos, by the graph, was there, right? X equals negative 2. But how do we get the zeros over here? And the answer, of course, is if you can't factor it, you always have the quadratic formula. And so the quadratic formula says x would equal negative b plus or minus the square root of b squared minus 4ac all over 2a. And so inside this square root here, I've got 9 minus 20, right? So I've got that negative 11. This is why I was getting the square root of a negative number, is why I'm getting imaginary roots. So this would be 3 plus or minus I square root of 11 over 2. So these are the 3 zeros. We've got one real 0 and 2 complex or imaginary roots.